In the first part of this afternoon, I want to talk about regression discontinuity designs. And so this is a very recent thing in economics, really. Although the basic methods go back to, I think, 1960, a paper by Thistlethwaite and Campbell, I certainly hadn't seen any applications in economics for a long time before 1997. But since then, there have been a lot of applications, a lot of empirical studies using these methods, as well as some theoretical work. So what I want to do in this lecture is talk a little bit about the basics of that, and then talk a lot about what I think are useful practices for implementing these designs, and sort of what kind of things can be done well. And in the end, my view is that this is actually an extremely important method in practice, one that has great credibility when it's applicable, and one that is in fact very widely applicable in economics. So after talking about the basics, I want to talk a little bit about graphical methods for analyzing these designs. I want to talk about the specific method for getting estimates, namely local linear regression, that is based essentially on throwing out observations far away from the discontinuity point. I'll talk about specifically choosing that point somewhat optimally, and I'll talk some about variance estimation and about methods for checking the validity of the design. But so when does this arise in practice? The idea here is that somehow the participation in a particular program that we're interested in evaluating is based on a criterion with a very clear cutoff point. So a particular program may only be open to people over 25, and as well as be mandatory to people over 25. In that case, the idea would be that you would just compare people very close to that age limit on either side, and use that to get a sense of what the effect of the program is. That's what is known as a sharp regression discontinuity design, where all individuals on one side of the cutoff point are participating in, and individuals on the other side are not participating in the program. Another, the probably more common version, is the fuzzy regression discontinuity design, where what you see at a particular value of this covariate, that the proportion of individuals participating in a program goes up discontinuously, jumps up, and the more, obviously, the better. In all those cases, the idea is to compare individuals just on either side of the cutoff point, and when this cutoff point is clearly exogenous and not affected by individuals, then that can give you a very credible way of estimating the causal effect. The key thing is that this may work very well in terms of getting good, credible estimates of the causal effect for a very particular subpopulation. But in principle, it doesn't really have much external validity. It's only valid at that particular cutoff point, and with the fuzzy regression discontinuity design, it is only valid for a subpopulation within that subpopulation. But the good thing is that for that subpopulation, it may be extremely credible. And in addition, the reason why we've seen a lot of applications, I think, in the last decade, is there's a lot of cases where these cutoff values exist. It's often very attractive for administrators to have very clear rules rather than discretion about who participates in these programs. And so some of the examples in the last decade that I think are very clear examples of this, and very credible examples, some of the work by David Lee, who looks at the effects of elections, where he's interested in what would happen if the election results had been different. And the idea there is to look at elections that are very close, where the winning candidate won by just a very small margin, but the election could have gone either way. And he looks at that, for example, to look at the effect of incumbency. There's some work by Angrist and Levy where they're interested in the effect of school size, and they exploit the rule that class size has to be less than or equal to 40. And so they compare cohort sizes close to the cutoff point. Even though that paper originally, also the published version of that paper, still sort of interprets that more as an instrumental variables design, I think that's really more usefully viewed as a regression discontinuity design. And I'll come back to the implications of that in general. There'll be more papers where people view the design as instrumental variables methods rather than being explicit about the regression discontinuity aspect of it. Another example is a paper by Sandy Black, who looks at housing values and how they relate to school quality, where the idea is to exploit the fact that schools have catchment areas, and so if you compare housing values on either side of the catchment area, of the boundary of the catchment area, you can end up with comparisons of houses that are actually very close physically, but that correspond to different schools, and you get arguably very credible estimates of the effect of school quality on housing values. And the last example, and I'll come back to that again as well, is one by Van der Klauw, who was interested in the effect of financial aid on acceptance, college admission acceptances, where he exploits the fact that the particular school he looks at puts applicants in a couple of discrete categories based on some numerical score, where the score is based on a whole bunch of characteristics of the applicant. But once you're in a particular category, your chances for financial aid are very different from individuals in another category, even though your actual score, and so in a sense your actual application, may be very similar. And so the last example is sort of useful because it sort of highlights that it's extremely important for those cases to look very carefully at exactly what determines the assignment to the program or the assignment to the treatment. Here it's the fact that these schools don't just look at the overall application, but they have the sequential procedure where they first put individuals in different categories, and so you end up with large differences in average financial aid offers for individuals who were very close in terms of characteristics. So let me set up the basic framework, and that's very similar to what we looked at this morning. And there's two potential. So we look at the effect of some binary program. There's two potential outcomes: y0 and y1. There's the causal effect we're interested in is the difference y1 minus y0. And there's a binary indicator wi, which is equal to 1 if the individual participates in the program, and 0 otherwise. What we observe is the triple yi, wi, and xi. And the key thing here is that at a particular value of the covariates, the incentives to participate change. They may change dramatically to the extent that all the individuals with a value of x less than this cutoff point c don't participate in the program, and all the individuals with a covariate value greater than or equal to c do participate. Or it may just be that they change somewhat more modulously, and what you see is a jump in the probability of participation, discontinuity in the propensity score at that particular value of the covariate. And so typically there's just a single covariate that drives this. In principle, it could be a function of covariates, but typically, I think all applications I've seen involve a case where there's an observed covariate. We know what the rule is. We know what the discontinuity point is, although we may not know exactly what the jump is in the probability. And so the first case I'll refer to as the sharp regression discontinuity design, and the second one as the fuzzy regression discontinuity design. So as an example, I'll sort of refer, I'll show some graphs actually from this paper by David Lee, who's interested in the effect of incumbency on election outcomes. And so the idea there is to use the elections where to compare subsequent elections in cases where the current election had an outcome that was very close to 50-50, where essentially who won was more or less random. And the idea is then going to be to compare subsequent election outcomes, compare the ones where Democrats won the first one with the ones where Republicans won the first one. So the key assumption that underlies this is that the conditional expectation of the two potential outcomes as a function of the covariance is continuous in X. Now, in some sense, this makes the assumption slightly more functional form dependent. And so, really, what is a more general version, a stronger version of this assumption, but one that's typically equally credible, is that the conditional distribution of y0 as a function of x is continuous in X, and the same for the conditional distribution of y1 given X. If that's if either version of that assumption is true, then what we can do is look at the conditional expectation of y given X and take the limit of X going from the right to the cutoff point and subtract from that the limit of the expectation of the regression coming from the left, and look at that difference as the causal effect, as the average effect of the treatment, as the average value of y1 minus y0 at that particular value of X. And so this is the first part where the external validity is sort of fundamentally limited. No matter how much data you've got, if there's only one cutoff point, you're not going to be able to say very much about the effect of the program for other values of the covariates other than at this particular cutoff point. Now, you may be able to do a little more. You may be able to condition on additional covariates and get a sense of how much variation there is in the treatment effect. But in the end, all the data are going to be informative about is about effects of the treatment for individuals close to X is equal to C. Second point is that this is fundamentally always going to rely on extrapolation. We want to compare the two limits of the regression function. We're going to need to use observations somewhat further away from these cutoff points. And one of the key issues in implementing this is trying to figure out how many observations to use on either side and how exactly to do the extrapolation. Ideally, obviously, you would just have individuals extremely close to X, so close that whatever the derivative of the regression function is, it's not going to affect things. And you could just compare simple averages on either side. But in practice, there's often a lot of concern that you may need to use too many observations, and you may want to use additional adjustments. And so we'll talk a bit about that. The second example is this fuzzy regression discontinuity case. So that there, I want to partly use the Van der Klauw example a couple of times to illustrate some of the issues. So he's interested in the effect of a financial aid offer by college on whether the individuals admitted actually accept their offer. I'll leave that there. And so the insight he had sort of bringing to this study is that the financial aid procedure has a lot of structure on it. Instead of just looking at the overall application and then deciding on the financial aid offer, it's streamlined by first putting the applicants in a couple of categories. So first, they assign numerical values to a whole bunch of characteristics of the applicants. Based on that, they put them in a couple of categories, and then they decide financial aid sort of first within these categories. And the result of that procedure is that the financial aid offer is very highly correlated with the category, even though the individuals in neighboring categories need not be particularly different in terms of these scores. And so there the idea is going to be to compare the individuals who are very close to the cutoff point for a particular category and compare them with individuals in the other category, but with more or less the same score. However, even though this changes the probability of financial aid considerably, it doesn't change it from 0 to 1. Individuals in both categories, or in all the categories that Van der Klaauw looks at, do have some chance of getting financial aid. And so we can't just simply compare the average outcomes in these two groups, but we need to adjust for the fact that the probability didn't change from 0 to 1. So in that case, what we do instead of just looking at the difference in the outcome, we divide that by the difference in the two limits of the regression function for the treatment indicator. And this is where it gets very close to looking to instrumental variables. And we'll make that connection very explicit in a little bit. But essentially, this is going to look like regressing the outcome on the treatment indicator using the indicator for x being greater than c as an instrument. And we'll exploit that connection. We'll explore that connection first and then exploit it more in some of the implementation. So the first thing I want to do is think a little bit about the interpretation of that and relate it to the instrumental variables literature. And this is one of the contributions of the econometric literature to this, as I said before. Well, there's a very old literature in statistics. And so one way to think about this is to think for each individual about let's do this in terms of the financial aid example. So the treatment indicator is a binary indicator for whether you get financial aid or not. The covariate here is this numerical score that is assigned to an individual's application. I think here about what financial aid, whether a particular individual would have gotten financial aid if the cutoff point for a different category would have been set equal to little x. I say that to be able to think about it, that really requires you to think about the possibility of changing the cutoff point. So suppose these scores are on a scale of 0 to 100. Maybe the current cutoff point is 60. Wi of x requires you to think about what would have happened with a particular individual had the cutoff point been 59 or 58 or maybe 62. And so the assumption we make here is that Wi of x is non-increasing in x at the particular cutoff point that is actually in place. Which means that if we lower the cutoff point, every individual would be more likely to get financial aid. So if you look at an individual, suppose the cutoff point at the moment is 60. If we move it to 59, someone who was already getting financial aid still gets it. But if someone who didn't get financial aid before because they had a score of 59 may now get it as a result of the cutoff point being lowered to 59. In that case, you can think about the individuals who are actually affected by the cutoff point. And I'm going to come back to this notion later this afternoon in the instrumental variables lecture. But the idea is that there's some individuals who are actually affected by the cutoff point. And so remember, in the fuzzy regression discontinuity design here, there's some people who get financial aid even with a very low score, even if they're below the cutoff point. There's more individuals, of a higher proportion of individuals gets financial aid if their score is above 60 than if the score is below 60. But in both groups, there's some individuals getting financial aid. The group we're most interested in here is the group that is actually affected by this cutoff point, who gets it only because they just ended up being on the right side of the cutoff point. And that's what we refer to here as the compliers. So these are individuals who only get financial aid if they're lucky enough to get in the high category, but not if they were in the low category. So suppose you think, and let me just make this more specific, because this is a very important point for the interpretation of these methods. Suppose that the individuals with very low scores who get financial aid get this because they're good at sports. They get the sort of a separate category of athletic fellowships, and so the individuals who are below the cutoff point of 60 will get financial aid, do so because they're particularly skilled in some other dimension that wasn't part of the overall score. Then in the end, this design is not going to be informative about financial aid for them. It's going to be informative about the individuals for whom the cutoff point matters, who only get financial aid if their score is just high enough to be in the category. That sort of makes sense, but in the end, depending on how big the jump is, there may be a relatively small part of the population. First of all, it's only individuals, it's essentially only individuals who score 60 or very close to 60 on this admission score, but even then it's only the individuals for whom a small change can make a big change in getting financial aid. So this is one of the main themes of this method, is that it may be extremely credible in getting good estimates for a particular subpopulation, but it may also be a very small, potentially not representative subpopulation, but in some sense it's all you're going to be able to get in all of these cases. So this is just repeating that. Now, let me make a second point, and that's relating this to the first lecture this morning. In the fuzzy regression discontinuity design, we do actually, if we look at individuals reasonably close to the cutoff point, we do actually have overlap in the covariates. If the design is really fuzzy rather than sharp, there's individuals getting financial aid in both the low-scoring group as well as in the high-scoring group. So in principle, we could have done an alternative analysis along the lines of the first lecture, namely assuming unconfoundedness, assuming that conditional on the test score who gets the financial aid is more or less random. And so there's nothing particular in the data that tells you that would be the wrong thing to do. It is going to give you a very different set of estimates potentially. It relies on a very different set of assumptions. And I think in cases where you see and where you have reason to believe, and so let me back up there. In the Van der Klaauw example, if the probability of getting financial aid had been a smooth function of your score, I think that would have been the natural thing to do. Compare individuals who get the same score, some of whom get financial aid, and some of who don't. At a point where you see that there is a discontinuity in the probability of getting financial aid as a function of the score, just comparing individuals with the same value of the score, but some of whom we get financial aid and some of whom don't, seems a very unattractive thing to do. In the end, what the regression discontinuity design suggests is that the individuals who get financial aid despite having a relatively low score are very different from the individuals who don't get financial aid and getting a low score. Now, for this particular example, you could disagree with that, but my main point here is that in this setting, you do actually have a choice in what methods you use. And in most cases, it's very likely that these methods will give you very different results. The statistics is not going to tell you what the right set of assumptions is here. I would strongly, in most of these examples, if there is a discontinuity in the propensity score, I would strongly suggest looking at this type of estimates rather than trying to condition on these covariates, unless you have a convincing story why there may be a discontinuity in the propensity score, even though these individuals are comparable. But again, the point is you have to make. There's a decision to make here. You have to think about the substance of the case in order to make that decision. And here, despite in principle the data being perfectly compatible with using unconfoundedness, here I would argue there's a specific reason why not to use those methods. Okay, then the next set of things I want to do is talk a little bit about doing graphical analysis. I said in some sense this is not a very deep point, and this is something that pretty much everybody does using these methods. What you want to do is look at the regression function and see whether there's actually any evidence of a jump at the cutoff point. So here's a paper that I borrowed from David Lee's paper, where he looks at the probability of someone winning the next election given the margin of the previous election. And so what you see is that the margin is, it's a difference between the winner and the loser. If it was just a little more than zero, if someone actually won if that person won the previous election, the probability of them winning the next election are far greater than if they just lost the previous election. And without doing any further analysis, this picture pretty much sums it up, that there's a very big effect of having just gotten those couple of extra votes on outcomes in the subsequent election. And so clearly one of the things you always want to do is look at the regression function as a function of the forcing variable, the variable that determines the assignment, and see what is actually happening at a cutoff point. Now, to be slightly more specific in the advice, I would be inclined to just use a very simple method for doing that, rather than smooth things using kernel methods. I would be inclined to just calculate averages in discrete bins, making sure that these bins don't cross the cutoff point. Why is that? It's partly to not be misled into thinking that there's a lot of smoothness away from the cutoff point that may not actually be there. If you use a kernel estimator to the left of the cutoff point and a kernel estimator to the right of the cutoff point, you're going to impose smoothness on both sides without imposing it at the cutoff point, and so it's always going to look as if there's a much bigger jump at the cutoff point relative to anywhere else. So instead, use something that is in fact much simpler. Just group the data discretely and see whether at the cutoff point there is a big jump relative to what you see everywhere else. If you can't see it with the naked eye, it may be possible that it's still there in the data, but it's clearly going to be much less credible than if you get evidence as clearly as that in the Lee example. So here is a case where I would fairly strongly encourage you not to use more sophisticated methods than just simple averages. The second set of plots that I think is very helpful, I'll later give an example of that also from the Lee paper. Look at other covariates. Here in these designs, the covariates don't actually play that big a role. In the end, almost always the story is that the covariates should have the same distribution on either side, but so close to the cutoff point. There should not be much difference in the covariate distributions by treatment. And so the covariates are not going to be particularly, not going to be necessary in general for consistency, for removing bias. But what you should, what they're extremely useful for is checking whether the design is credible. And so what you should plot there is essentially the same graph I just described for the outcomes, but using the other covariates. And if you find that there's a jump there at the cutoff point comparable, sort of bigger than jumps at any other value of the covariates, then there's a problem that needs to be explained. It may well be that, well, actually, let me take that back. I've not seen any examples where there was a convincing story for other covariates to change at that cutoff point. And so it's pretty much if you see the substantial jump in any other covariates, it suggests something's wrong with the design. And so you can do that the same way, kind of just using these bins. There's no particular reason to impose smoothness. In fact, it may hurt. Last thing, last plot. This is really based on a suggestion, also based on work by Justin McGrary. Is to look at the density of the forcing variable, the variable that determines the assignment. The idea there is, and I'm going to come back to that. Well, actually, let me talk a little bit more about it here. But the idea there is that you would be concerned if there's a discontinuity in the density of this variable at the cutoff point. And the concern would be that individuals, or that someone in the whole process may have been successful in manipulating this variable. So in the college example, suppose that this college actually announced that sort of their financial aid categories were based on whatever SAT scores, and that in fact the cutoff point was 1200 on the SATs, and suppose it was possible. Suppose individuals could retake those things. I'm revealing my ignorance here of the American high school system. So that I don't actually know what the relevant scales for these scores, or whether you can retake these. But you could imagine that if the process is, if individuals know what the cutoff point is, and if there's some way they could affect their cutoff point by retaking an exam or manipulating part of their application, what you might find is that there's more individuals just to the right of the cutoff point who are happy with their score, and that individuals just to the left of their cutoff point find some way of moving up by trying again. Most sort of very interesting example of that, and this is actually sort of tribute sort of to how fast some of these methods travel these days, given that I hadn't seen any applications in economics before 97, but this year there were actually two potential graduate students that I talked to during the recruiting process, we had very interesting papers using regression discontinuity designs. And there was one, Joe Shapiro, who had a paper looking at the return to education in using compulsory schooling, identification strategy. So this was data for, I think, Argentina. And so the cutoff date there was July 1st. If you're born before July 1st, you would go to school earlier than if you were born just after that. Sort of similar to the Angus-Kruger identification strategy. But so what they found in that paper was that there were a lot more births just before July 1st than there were just after July 1st. Now, sort of before looking at that, you might have thought that the date of birth would have been very hard to manipulate, but I think, and so I'm not sure I get this completely right, but I think the story was partly that there was a substantial number of induced cesarean section birth that moved the birth up, and that hospitals essentially encouraged people to be aware of the cutoff date there. And so the key thing is that even though you don't actually need the density to be smooth around the cutoff point for this design to be valid, there's nothing we're assuming about the density. If you find that there's a discontinuity in the density at that particular point, it's just very hard to understand where that could come from without being concerned about individuals manipulating the covariate value. And so the third plot that is extremely useful in order to build credibility for a particular set of estimates is to plot the density of X and look at discontinuity there. And if there is one there, you should have a story to explain that. Otherwise, it's hard to believe the results. Okay, now let me talk specifically about methods for implementing this. And so let me first talk about the sharp regression discontinuity design. And so essentially all these methods are non-parametric regression methods, but I'm going to simplify them considerably by only using uniform kernels or rectangular kernels, which basically means I'm just going to throw out observations that are more than some amount h away from the cutoff point. In principle, you can do slightly better by using more complicated kernels. You can try to make that very complicated. But the key word there really is slightly. The gain in the end, I think, from trying to be very sophisticated on the kernel is very minor here, and you lose a lot of the transparency. I mean, that's not always the case, but here the key thing is that there's just a single covariate, and there's a very specific object we're interested in, namely the difference in these two regression functions on the boundary of the support. And so just a simple kernel regression where with a rectangular kernel would amount to just taking the average of the observations within some amount h from the cutoff point. That doesn't work very well. The reason it doesn't work very well is we're trying to get the regression function at a value c using only observations to one side of c. This would work very well if we could use observations on both sides of the cutoff point for estimating the regression function. But on one side, the observations are in a different group. So to get rid of, and so the way that shows up is that you get very slow convergence rates for estimators of this type. And so what works much better is to use local linear regression. Instead of, the way you can think of the first estimator as locally fitting a constant, what you can do is take these observations between c minus h and c and fit a linear regression function to that to those observations, and then predict what would happen at the end, at the cutoff point. If you set it up the way I did here, where you specify the regression function as alpha plus beta times xi minus c, the prediction at the cutoff point is just alpha. And so you just use the regression part to remove some of the bias. Now you can simplify that further and just put it all in a single regression function where you put in an interaction, where you put in a dummy for the treatment, as well as an interaction between the xi minus c, between the covariate centered at the cutoff point and the treatment indicator, and then the least squares estimate for tau gives you the local linear regression estimate based on this particular set of observations. And so once you set it up this way, it's clear that you could very easily include other covariates as well, and that should work fine. The key point I'm going to come back to in a second is how to choose the bandwidth h here, which is just how far you extend the set of observations you're using here. Just before doing that, I want to just set things up for the fuzzy regression discontinuity case as well. There, the idea would be to use local linear regression for both the treatment indicator and the outcome, and do estimate the two things separately, take the ratio of them, and that gives you the thing at the bottom. The advantage, so one advantage of using the rectangular kernel here is that we can, previously was that we could just interpret it as doing OLS. Here, the advantage is that we can, in the fuzzy case, we can interpret it as doing two-stage least squares, where we're trying to estimate the regression function given there in the 2SLS equation, using as the instruments VI and the indicator for for xi being greater than c, and that's going to help us estimate the variance as well using this interpretation. Again, adding extra covariates here is going to be very straightforward in this two-stage least square setup. Next thing I want to spend a little bit of time on is choosing the bandwidth. And so partly this follows a working paper by Ludwig and Miller. So there's a very large literature in general on choosing bandwidth in non-parametric regression. But so there's two things here that are different. One is we're interested in the regression function at the boundary of the support. And so almost all the results are for the interior. And the second thing is that we're interested in the regression function at a point rather than at fitting a regression function everywhere. And again, the standard cross-validation methods and optimal plug-in methods are based on criteria that minimize things like integrated squared error. And here, they may still give you a perfectly reasonable result, but it's very specifically not what we're interested in. We're only interested in this difference in these two regression functions at a particular point. And so what I want to do here is sort of talk about a cross-validation type method that is geared specifically to those circumstances. And so in order to set it up, unfortunately we do need a little more notation here. Now for all values of x in the support, I want to think about estimating a linear regression function from the left and from the right. By estimating it from the left, I mean using all the observations within a bandwidth h to the left of that cutoff to that point x. And by estimating it from the right, I want to use observations to the right of that particular value x, but within a distance h. Then, and at a particular point x, we then estimate the the regression function by the intercept from that local linear regression if we're to the left of the cutoff point, and by with the intercept from the alpha r if we're to the right of the cutoff point. Now we can think of looking for a cross-validation criterion that minimizes the sum of the squared differences between the actual outcomes and the estimated regression function, but the regression function is sort of always based either on observations to the left or it's based on observations to the right of the cutoff point. And so that deals with one issue, namely the fact that we're interested in estimating something at the boundary. Now, when we're doing the cross-validation, every time we only use observations on one side of the particular observation. It still doesn't deal with the fact that we're just interested in the regression function at a particular point. If we average this criterion over all observations, we would still be letting things be determined potentially by the tails of the distribution, where in general you're going to not be able to estimate the regression function very well. And so if you use cross-validation there, it may well suggest using a lot of observations because there's few observations in that area. And so instead of doing that, the suggestion here is to average that square difference between the outcomes and the estimated regression function, but only do that somewhat close to the cutoff point. So maybe on both sides of the cutoff point, throw out 50% of the observations in order to estimate the optimal bandwidth. But somehow make sure that things don't get that the bandwidth the choice doesn't get driven by the tails of the distribution, which would tend to lead to much bigger bandwidth choices than would be optimal in the center of the distribution. So here, that second part deals with the second concern, namely that we're interested in only at what happens to the regression function at C rather than all over the support. Now that was essentially for the sharp regression discontinuity design. For the fuzzy one, in principle, you could do this separately for both regression functions. You could even choose a different bandwidth for both. In practice, that sort of makes things very awkward, and so I would be inclined to just choose the smallest of the bandwidth, and which would, in a sense, focuses mostly on bias rather than variance. And in fact, I would be inclined to just calculate the optimal bandwidth only for the outcome and ignore the one for the treatment indicator. The one for the treatment indicator the optimal bandwidth there would tend to be much bigger anyway. It would typically, the jump there is much bigger, and the regression function would be flatter away from the discontinuity point. And in fact, if you're close to a sharp regression discontinuity design, the regression function would be completely flat in both cases. But so in practice, you would want to use, I would recommend using the same bandwidth for both and just estimating the optimal bandwidth on the outcome regression function. Okay, variances. One's the easy way. So the hard way is sort of somewhat useful for actually thinking about what the variance looks like. This is essentially taken from the Hahn-Todd-van der Klauw paper, where I've simplified things by using a rectangular kernel. And so what you can do is just look separately at the variance for the difference in the regression functions for the outcome and for the treatment, as well as the covariance. Okay, so talking here about estimating the variance, you can decompose the variance using the variances for the outcomes and the treatment indicator, and put it all together. So one way of actually estimating the variance in the end is to just estimate all these different components, which here largely means the covariances and these variances. And this is also based on using a bandwidth that goes to 0, that essentially implies we can ignore the bias, which we cannot estimate anyway. So that's what you have to do in practice. Second way of estimating the variance, and that really relies very heavily on using the rectangular kernel, is using the fact that here the estimator can just be written as a two-stage least squares estimator, conditional on the bandwidth and conditional on using a rectangular kernel. So we're just using this smaller sample with observations where x is between c minus h and c plus h, using the indicator for x being greater than c as the instrument, the treatment as the endogenous regressor, and this interaction as this, the difference between x and c, and the interaction of that with the treatment indicator as the exogenous covariance. And so if you use the robust variance for two-stage least squares, you would get the same in the end as what is described on the previous slide. Okay, so now let me talk a little bit about specification checks. And so there's basically two concerns in the application of these methods, be it the sharp or the fuzzy design. First possibility is that there's other changes at the same cutoff value of the covariate. So if in fact this particular age limit makes you eligible for one program, it may also make you eligible for another program. And so there may be other changes in individual's environment, and attributing all the changes to the one treatment you're looking at may not be correct. And the second concern is that somehow individuals are able to choose the variable, the value of the variable that determines which side of the cutoff you're on, in a way that invalidates the whole design. So what can we do? So some of these things I've talked about already. The first is to look at this, to investigate whether there's discontinuities in some of the covariates. I've never seen a case where there was a convincing story for having a discontinuity in any of the other covariates. And so if you find one, you should either be able to explain it or be concerned about the credibility of the estimates. Second one is the McCrary concern about the discontinuity in the distribution of the forcing variable. Third, you may also want to see if there's discontinuity in average outcomes at other values. And so the graphical analysis that we talked about before is very helpful there. But if the graphical analysis isn't conclusive, you may just want to test at different values and see how whether anything comparable to what you find at the cutoff point is there. You may want to check how sensitive things are to the bandwidth, and then you may, if you have discrete data, you may want to sort of think a little bit more about the variance. Let me talk about it in a second. So this one is we pretty much covered. What you want to do is the same way we did in the unconfoundedness, in the analysis on the unconfoundedness. You want to estimate an effect that you know is zero in order to see whether the methods are working. And so here's an example of that from the Lee paper, where he looks at election outcomes prior to the one that was very close. And there what you see is sort of, even though this regression function isn't of any substantive interest, what is of interest is the finding that around the cutoff point, this is actually a smooth function. If there was a big jump here, you would be concerned that somehow these districts that were on one side of the cutoff point were substantively different from the ones that were on the other side of the cutoff point. It would be very hard to come up with a story why that would be the case. But in other settings, there may be considerable concern with that type of misspecification. The second one we talked about a couple of times as well is looking at the distribution of the density of the covariate. You may want to test whether this discontinuities in average outcomes at other values of the covariates and to get a sense of whether the statistical methods are working well. Again, here you would end up with estimating something that you know is zero and finding something that is close to zero statistically and substantively makes these estimates the overall estimates more credible. Even when you choose the bandwidth optimally, you should always check how sensitive the results are for this, and just put in half or twice the original bandwidth. Last point is, in practice, there's a lot of cases where the covariates are actually discrete, and sometimes they may be close to continuous, but in some cases they clearly are very discrete. And so even though you may try to compare outcomes very close to the cutoff point, you may end up comparing average outcomes for values of the covariates that are somewhat far away from the cutoff point. And so one way of trying to see whether that is a concern is an idea from Lee and Cart. We put a more parametric specification on the regression function and then use the difference between that and the average outcomes as a specification error that allows you to adjust the standard errors and get more credible confidence intervals. Okay, I think I'm running a couple of minutes over, but this seems a good time to stop here and see if there's any questions, and otherwise adjourn for 15 minutes. Yes?
You mentioned that the cutoff rule could be a function of covariate. Suppose we're in a world where either the nominal cutoff rule that we think is the cutoff rule is not the actual cutoff rule that is the true cutoff rule that's being followed, or even in the extreme case where we actually don't know what the cutoff rule is there a way of either graphically or econometrically or statistically of legitimately finding a cutoff rule, either one that's a value of one covariate or a function of covariate?
Yeah, so let me just go back to the first Lee graph. So here this is obviously a case where you actually know exactly what the cutoff point is. And so now suppose you legitimately don't know what the cutoff point is, but there's strong evidence, you have strong prior knowledge that there should be one. Then you could actually estimate it, that there's methods for estimating structural breaks that would allow you to do this. I'm sort of somewhat skeptical about the empirical relevance of that setting. I mean, I've not seen a good example where you really legitimately know that there is a cutoff point, but it's impossible to actually, by sort of prior to looking at the data, but by just investigating the process, where it's impossible to figure out what the cutoff point should be. I mean, you could imagine that somehow it got lost, that it was a recorded value, and that somehow it got lost. But unless you can see it pretty clearly in the data, I think in most cases you would see it pretty clearly in the data, and you could estimate it and pretty much ignore the uncertainty coming from that, because it would be of lower order anyway, and the jump should be high enough, should be big enough for that for that uncertainty not to matter much anyway. If you really relied on searching for the cutoff point, and it was not completely clear where it is, I think it's very hard to imagine the eventual estimates having any precision. Because at that point, if there's a lot of uncertainty about where the cutoff point is, these estimates are never going to work. No other questions? Okay, so we'll start again at 3:15.